So hello, in this video I'm going to go over a dynamics question which involves some resolving on an inclined plane with kinetic particles. It's fairly standard in that we've got to work out an acceleration and a tension, and typically we'll have a simultaneous equation where tension eliminates by adding the two equations. So it's a fairly normal situation. Any of you who've watched the videos previously made a big point of coefficient of friction, and the equation F is less than or equal to mu r, but happily in a dynamic situation where things are moving, F equals mu r if moving or on the point of moving. So that makes life, or in limited equilibrium, so that makes life a little bit easier in these situations. Although there's more equations to work with, we can at least be, the model basically is simpler from a frictional point of view, because that's just equal to mu r. You just have to get in the right direction because it goes to oppose motion. Now in this situation, it's fairly clear from the situation, I would think, that it's going to accelerate this way because of the 10 kilogram force downwards. If you get it wrong for some reason, you're just going to get a negative answer, but it's fairly clear acceleration is going to go that way. We're going to assume it's the same both sides of the pulley, and that the thing that makes that kind of assumption viable is the fact that it's inextensible. So, you know, this, for every bit this moves up, P moves up, Q will also move down. So we could assume the acceleration is the same both sides of the string. And we can also assume that tension is the same on both sides, and that's all to do with the fact that the pulley is smooth. Okay, one of the most important things with these things is to do a good diagram. So let's just do that. First of all, we've got our normal contact force, as we always do when we've got connected particle. When we've got something in contact with something, there's a normal contact component. Even if it's smooth, we have that. And here we've got a weight. Let's call the weight 5g. Okay, 5g, where g is the acceleration due to gravity, which on Earth is around about 9.8, 9.81, but we normally take as a default value 9.8. Anyway, it's helpful to work through with g here, because g means that it's more elegant and precise, so we can give an answer in terms of g and then actually work it out, so we kind of get the best of all worlds if we work with g throughout our equations, rather than just work it out at the beginning. The weight at the beginning, the weight is that 5 times 9.8, which would be 49 newtons, but I'm going to work with the 5g. Weight is approximately 49 newtons, but I'm going to work with the 5g. The other thing is a little bit of just angle work, you know, alternate angles or whatever. This angle will be alpha, which will always be the same as that. So other forces, well, the tension will be the same both sides of the string, provided the pulley is smooth, or when we say smooth, we don't mean the surface is necessarily smooth. That would be more like a peg. It just means that there's no inhibiting factors. There's nothing slowing it down, like the mechanism, the ball bearings or whatever, aren't actually inhibiting motion in any way. So we've got tension pulling this one up and tension pulling this one down. And then we've also got friction. We've got friction. In this case, as I say, because it's moving, we could just go straight to mu r. We are already told what mu is. Mu is 0.2. And in this case, we can say F equals to mu r. So we have 0.2 r on our diagram. Or you can put in your working on your equations if you prefer. But it's a fairly straightforward with friction now, just as long as we have the direction it opposes motion. And it's the normal contact force, or the reaction force, times by 0.2, because that's the coefficient of friction. Right, so let's write our equations down. The first thing, resolving perpendicularly to the slope. If we do that for P, if we do that, we've got three forces in play. The reaction force is going upwards. And then we've got the component of the weight going downwards. And because it's next to the, I might go to a different colour here, because it's next to the marked angle here, that component there is 5g cos alpha. We do know alpha, but I'm just leaving it for the time being, so to put into equations later, just to make it a little neater, rather than have horrible kind of numbers around which are unrounded, which are rounded and whatever. So I'm just going to put alpha in my equation. So we've got r minus 5g cos alpha, which is going into the plane, equals to 0. They're balanced out. Or if you prefer, you can just go to forces up equal forces down. You can go straight to that if you prefer. Equals to 5g cos alpha. Right, now I am going to do a bit of work with the angles now at this stage. Tan alpha is equal to 3/4. A bit of trigonometry. I like to go to the 3, 4, 5 triangle, but working out on your calculator these days is fine as well. 3, 4, 5. Then we can say that sine alpha is equal to 3/5 and cos alpha equals 4/5. So I'll put that in now. So that actually gets us 5g times by 4/5, which is equal to 4g. So I'm now working with p still. So with p, we're going up, there's acceleration up the slope. So obviously it won't be balanced out, but then we've got basically one force going up the slope, that's tension. Remember, we're only looking at p here. We'll deal with q later in a separate equation. Don't attempt to do it all in one equation. It will be disastrous on these cases. So we are just dealing with p. So we've got t going up the slope. Down the slope, we've got the 0.2r, which is going straight down the slope. And we've also got the component of the weight down the slope, which is, in this case, 5g sine alpha. 5g sine alpha because it's away from the marked angle alpha, and we've got 5g cos alpha into the slope. These two things you're often going to see with components of weight perpendicular and parallel to the slope. So down the slope, sine, into the slope, or perpendicular to it, cos. So anyway, so we can readily work with that. It's also going in the opposite direction to the acceleration, so it's minus 5g sine alpha, but it's not equal to 0 now because it's accelerating, so that's equal to 5a, not 5ga as I've seen, 5a. G is what we do to work out the weight. So this is mass, so in our F equals ma equation, we've got F, which is the overall force up the slope, m and a. And the mass is 5. The weight is 5g, but it's mass times acceleration. So no g on the right-hand side. Okay, so that's our equation for p. I think it might be useful to combine these two now, because we know that r is equal to 4g. This is my frictional force. It is unfortunate sometimes that F is used for different things. That's frictional force, 0.2 mu r, or friction. So we can actually put in our value for 4g, and we can also say that sine alpha is 3/5 as well from this point. So let's just tidy that up a bit before we actually do any more equations. I like to do that sometimes. So t minus 0.2 times 4g minus 5g times by 3/5 equals to 5a. Okay, so this is 1/5, so that's 4/5 minus here this is 4/5 minus 15/5, so that's 19/5. So t minus 19/5g equals to 5a. So that's going to be a pretty useful equation that I'm going to use, because I've got t in terms of, and you're going to see this is a pretty common scenario here. That's just dealing with p. So for the whole lot of this, that's a perpendicular. We've kind of done three things really. We've resolved perpendicularly, we've resolved parallel to the slope. Okay, we've resolved parallel. And we've also used f equals mu r. So we've kind of, the combination of those three things has got us to this, what will be quite a useful equation in the grand scheme of things as we go to the next bit. Right, so now a far easier equation, in fact, is going to be for q, because there's no kind of components that we need to consider. We've got weight going downwards, which is 10g, and we've got tension going upwards. So we can just apply F equals ma to P, to Q, should I say, and you will get 10g minus T is equal to mass, which, remember, mass doesn't have a g in it, it's 10a. So that's our second equation, and it's going to be very useful. You will often see in these scenarios, not always, but it'll be useful to add these two, because t cancels if we add the two. So it's a simultaneous equation, and quite commonly adding will eliminate t. So if we add the two equations, we get 10g minus 19/5g, t having cancelled, is equal to 15a, those two added. Okay, so if we work all that out, that's 50g minus 19, which is 31g. 5 times 15 is 75g. So we've got a is equal to 31g over 75. It is sometimes acceptable, it's sometimes advantageous even to have g, because g is universal, it's a universal constant, so this makes this in some ways more precise, because it's dependent on g, whatever it is. G on Earth varies between about 9.78 and 9.9, I think, something like that, depending on whether the closer to the equator I think you are, the lower it is, and also altitude has some bearing on things. But anyway, it's not, in mechanics we normally take it as 9.8. I think it's on average just over that, and I think closer to 9.81, but not that much. And I think in physics, for those who do physics, they take 9.81 as a measure, but it's not exactly totally an exact thing, and it does vary. So there are advantages to have it in g, but often we do want, personally I'd do both. If we have three significant figures, it'd be 4.05 meters per second in some way. If you're or for to two significant figures, in some ways 2 would be more appropriate. If you're using 9.8, 4.1 meters per second, or meters per second squared, should I say. Right, getting the units right. Okay, so meters per second squared. So that's the acceleration. And so now it's just a case of, that's part A done. And the second bit is finding tension. They often ask for tension. Once we've worked out the equation, the tension, we can, the acceleration, we can easily work out the tension. So I'm going to go back to this equation. So substitute back. Substitute A back. I can substitute into the other one if I want, but that one looks a little bit easier because t is positive. Not make a big deal, but I'll substitute into that one. So we'll get t minus 19 over 5g is equal to 5, and now I really do want to put an exact answer in, or at least the one I've stored on the calculator, not these two rounded answers. So it's 5 times 31 over 75g. So that's going to be t minus 19 over 5g is equal to 31 over 15g. And then that is going to come to, if I take that over to the other side and put over a common denominator, 3 times 19 is equal to 57 plus 31, which is equal to 88 over 15g, which again is some advantages to having an exact answer like that. Just check that's right for a moment and give to 3 significant figures or 2 significant figures. As say, I think it's a good idea to be in the habit of doing all of these things, because sometimes they will prefer, but depending on the question, it'll be preferred to have an answer in terms of g. So that's equal to 57 if we're going for 3 significant figures, which if you're using 9.8, which we not normally are in mechanics, 57.5 newtons, 3 significant figures, or 57 newtons, which is probably more appropriate if we're using 9.8 for 2 significant figures. So this is the exact, and the advantage of this is that g can, it's dependent on g, which can be helpful because g isn't an exact thing. So that gives a nice exact answer. It really depends on the question. I'm finding in mechanics more recently they want a rounded answer, so you really need to be careful of answering the question in hand. Can't go too wrong by giving 2 of these. I would have thought this and this would be, if you're using 9.81 then use the 3, but in mechanics they normally say, in our exam they normally say 9.8. I often say 9.81 for the benefit of the physicists because that's what they use, but please be aware it's not actually 9.81 either, not universally. Okay, thank you very much, bye.